Hello and welcome to helpyourmath.com. In this video, we are going to go over the first three properties of exponents: same base multiplication, power to a power, and the distributive property. First up, we have same base multiplication. We're going to talk about why the shortcut or the property works, and then we're going to actually identify what the property is. So with same base multiplication, let's see if we can figure out how to go from 5 to the 5th times 5 squared to the final result where it's just 5 raised to 1 power. So what we're going to do is we're actually going to use the definition of exponent, which is to rewrite it as multiplication based on what the exponent is. That's the number of times we need the factor. And I'm going to do 5 to the 5th in red, and I'm going to do 5 squared in green, just to really keep them separate. So 5 to the 5th, that means rewrite that base 5 times via multiplication. 2, 3, 4, 5. While the green, 5 squared, we want 2 more factors of 5. You'll notice here that when I write it as multiplication, now everything is multiplication, right? Because that's what exponents are. They're repeated multiplication, then we were already multiplying anyway. So now, how many 5s are being multiplied together? Well, let's count. We have 5 from the red and then 6, 7. So that's a 5 being multiplied to itself 7 times. We would write this as 5 to the 7th. So looking at the exponents that we started with a 5 and a 2, and then our end result was a 7. Well, what's the relationship between 5 and 2 and 7? Sure, 5 plus 2 equals 7. Okay, all right. So maybe that's a thing. Let's look at it again with these a's. So we have a squared times a to the 4th. I'm going to do my a squared in red, my a in green, and my a to the 4th in purple. So a squared, that would be a times a. The a is just times another a. And then the a to the 4th would be 4 factors of a, 2, 3, and 4. And now if we count all the factors of a that are being multiplied together, I count 1, 2, 3, 4, 5, 6, 7. Okay, so is there a relationship here? We started with an exponent of 2. Here we have an exponent of 4. What about that a in the middle? That's that invisible exponent. It has an exponent of 1. And if we add these together, we do end up getting 7. So the system works. And that absolutely is the shortcut for what we call same base multiplication. It's the same base because it's that big thing that's the same, right? In the first example, we had bases of 5s. In the second example, we have bases of a's. And so what we could say is that if we have some base and the same base and they're being multiplied, we can skip that middle step. We don't need to expand. We can add the exponents. So let's apply this property. Remember what we do. We're going to add the exponents. So we have b to the x times b to the y equals b to the x plus y. And of course, the more comfortable you get with these, the more steps you can skip. If you forget, you can always expand and count, although in this first example, I'm not sure I want to expand. X to the 11th, that's 11 factors of x. That's a lot of x. Yikes. So we have the same base, right? We have base x and base x. What do we do with these exponents? We add them together. 7 plus 11 is 18. So we would say x to the 7th times x to the 11th. That's actually going to be 18 factors of x. In the middle, we have m to the 9th times m to the 13th times m to the 10th. Since they all have the same base, we can apply the same base property where we can add the exponents. So we can write this as m to the 9 plus 13 plus 10 power, and that would be m to the 32nd. So if we were to expand this and write out all of these factors of m, we would have to write 32 m's total. This shortcut is beautiful. In the last example on this page, notice that we have 2a cubed. 2 is the coefficient, and it does have its own exponent. So 2 is separate from the a cubed. That's 2 times a cubed times b to the 4th times a to the 11th. So we see this string of multiplication. We have 4 different bases in this case. 2 is its own. It has its own exponent. When we go to combine, we're looking for same bases. The a cubed and the a to the 11th are the only same bases that we have. Everything else we would just bring down. We would have 2, and then when we combine the a to the 3rd times the a to the 11th, the commutative property says that I can kind of, multiply the things that do fit together, like the base a's. And so we could go off to the side and say this will be a to the third plus 11, and there will be 14 factors of a. So 2a to the 14th, and then we just bring down that b to the 4th. The next property we're going to look at is called the power to a power property. And again, this is nothing but a shortcut. If you ever forget a shortcut, you can always just do what the thing says to do. So let's see how we can find the shortcut for our power to a power. Okay, so we have 5 cubed, that's the base, and then we have a square, so the square means write the base twice. This would be 5 to the third times 5 to the third. Wait a minute, we just did this. This is same base multiplication, right? I have 2 base 5s being multiplied. What do we do with the exponents? We can add the exponents, and we end up with 5 to the power of 6. So what we're looking for is we're trying to figure out how can we go straight from this expression over to this expression. So what's the relationship between the exponent 3, exponent 2, and our final exponent 6? Well, 6 is 3 times 2. So maybe that's a thing. Maybe we can multiply the exponents. Let's look at our next example. J to the 4th is the base, and then we're cubing it. So in this example, we could write this as j to the 4th times j to the 4th times j to the 4th. We have 3 base j's, so that'd be j to the 4 plus 4 plus 4, and that would be j to the 12th. So did it hold up again? Could we go right from here to here? Sure, 4 times 3 is 12, and yes, this will always work. This is our next shortcut. For power to a power, we can write it as one exponent by multiplying the exponents together. So if we have b to the x raised to the power of y, we could rewrite this as b to the x times y. Okay, let's put this shortcut to the test. So remember what it was? It's b to the x. There's our first power. Being raised to another power, we multiply the powers. So here we have 4y to the 4th squared. That would be y to the 4 times 2. That's going to simplify to y to the 8th. In the middle, we have 2 sevenths cubed to the 8th. So this is going to be 2 sevenths to the 3 times 8. That's going to be 2 sevenths to the 24th. I'm keeping the 2 sevenths in parentheses just so it's very clear that it's not 2 to the 24th over 7. So I'm just trying to really make it clear what exactly is being raised to the 24th. Technically, we don't need the parentheses, but it's nice to see. Oh my. So in this last example, we have a little bit of work to do inside the parentheses. We have same base multiplication. And what do we do for same base multiplication? That's right, we add the exponents. So 2 plus 5 is 7. So inside we have c to the 7th, and that's being raised to the 5th power. Well, that's going to be c to the 7 times 5, and that's c to the 35th power. And there we have same base multiplication. Last up, we have the distributive property of exponents over multiplication. So you've probably heard of the distributive property before. We have a distributive property for multiplication over addition or subtraction, and here we have the distributive property of exponents over multiplication. And again, we're going to look for the shortcut here. Simplify each expression, multiply the numbers if appropriate. Okay, so this time we have this thing inside the parentheses, so that would be our base. Our base is 1/2 y. I'm going to write it 3 times. 1/2 times y once, 1/2 times y twice, 1/2 times y 3 times. Now I'm going to use another fun property called the associative property. We're going to kind of just put all my halves together because everything here is being multiplied, right? That's 1/2 times y times 1/2 times y times 1/2 times y. So I'm just going to kind of like rewrite it so I have my 1/2 times 1/2 times 1/2. And then here I have y times y times y. So that's what the associative property allows me to do. Wait a minute. But 1/2 times 1/2 times 1/2, that's 3 1/2s. So that could be, we could write this as 1/2 cubed. And then y times y times y, that's repeated multiplication. That would be y cubed. So what happens with this distributive property? Each unique base gets an exponent. It's a little bit like Oprah, like you get a 3 and you get a 3. And that's it because there were only 2 bases. So very minimal Oprah here. And it does say multiply the numbers if appropriate. I think this is okay for now. We could also say that 1/2 cubed, that's up here, 1/2 times 1/2 times 1/2. That's the same as 1/8. So you could write this as 1/8 times y cubed. In the second example of our distributive property of exponents over multiplication, this time the base, the thing inside parentheses, is m squared n, and we want 4 of these. So m squared n1 times m squared n2 times m squared n3 times m squared n4. And again, we'll use that associative property to just kind of lump together all the m's. So we have 1, 2, 3, and 4. 1, 2, 3, and 4. And now I have these same bases. I have 4m squared, so that's 2 plus 2 plus 2 plus 2. Well, that's going to be m to the 8th, right? Same base multiplication. I'm going to add the exponents. And then here I have 4 factors of n, so we would say n to the 4th. So how does that relate to what we were given? Yeah, we want to distribute the exponent to the exponents of the bases. If there's an invisible exponent of 1, you might want to write it just as a reminder, like, oh yeah, I need to raise this to that power of 4 as well. It doesn't become a coefficient. We don't multiply the bases by 4. We would then use the power to a power and multiply the exponents only. We only multiply the exponents by 4. So the shortcut for distributing power to a power, for distributing a power to a power is each base, we would do the power to a power for each unique base. So if we have a, b to the x, we kind of distribute it to each exponent, b to the x, a to the x times b to the x. If a had an exponent, we would then use power to a power and multiply the exponents. All right, so we're going to put this all together. Just to review, we had our same base multiplication. And again, we want to, I find it, for me, it's very helpful when I say things out loud. So that's why I constantly say these things over and over again, because that's like, I want to take my time. I don't want to make any silly mistakes, because with this like repeated multiplication, it's very easy to do. So we just want to take our time, come up with a strategy that works for us. So if we see the same base, we would add the exponents. This would be b to the x plus y. When we have power to a power, we multiply the exponents. So if we have b to the x to the y, this becomes b to the x times y. And then if we have the distributive property of exponents over multiplication, this is where we want to make sure each unique base gets that exponent. So a gets the exponent of x and b gets the exponent of x. Okay, so let's look at these 5 examples, and then there's a little challenge at the end. I always encourage you, pause the video, try these first, and then compare your notes with me. Okay, let's see how you did. In the first example, we have 4v as the base, that thing's being squared. When there is something like this square, because it is just a square, you could just write it twice, and that way you won't make any mistakes. Because a very common mistake is to just lump the 4 with the v, where 4 is not independent, it's not its own thing. But it is its own thing. 4 does have its own exponent. 4 has an exponent of 1. V also has an exponent of 1. So they each now get raised to the second power. We distribute to the 4, we distribute to the v, and we get 4 squared v squared. And we can actually do 4 squared. That's 4 times 4, which is 16v squared. So very common mistake is we just give v the square, and we're like, no, 4 is done. It's all set. No, it's inside the parentheses. It also gets squared. In this next question, how many unique bases are there? If you said 3 or 4, you would be correct. So it depends on what you want to do with that negative. Do you want it to be -3? Or do you want it to be negative all by itself and then 3 by itself? It doesn't matter. In this case, it doesn't matter which way you interpret it, because either way, if you interpret it as -3, we have 4 factors of -3. So this would be -3 to the 4th. And then this would be m cubed to the 4th. When it's power to a power, what do I do with that 3 and that 4? I multiply it. We get m to the 12th. And then here we have n squared to the 4th. That would be n to the 8th. We do want to clean this up. Negative 3 quantity squared is 81, and then we would have m to the 12th, n to the 8th. If you did separate the negative from the 3, that would be negative 1 to the 4th, and then 3 to the 4th, and then the m and the n would stay the same. Negative 1, if negative 1 is being raised to an even power, it's going to be positive. That becomes positive 1. We can drop the 1. That becomes our invisible factor. So far, so good? Let's look at the next one. So the next one, we again have power to a power, and again, we have this negative. So whichever way you like better, if you want to lump it with the 1/4, you can. If you want it to be its own thing, you can. Maybe it's like nicer if it's just its own separate thing, and then we can just worry about it. You know, basically it's deciding whether this thing is going to be positive or negative. That's all that negative is doing. So if I keep it separate, it's going to be negative 1 squared. Then we have 1/4 squared. Then we have, so I got to the negative, I got here, a cubed squared would be a to the 6th, and b to the 4th squared would be b to the 8th. Negative 1 squared is 1, so this is our invisible factor of 1. We can ignore it because there are other factors. If everything else canceled, we would need to say 1, but since there are other things still here in this problem, we will write those things. 1/4 squared, that's 1/4 times 1/4, which is 1/16. And then we have a to the 6th, b to the 8th. And this would be my final answer here. Okay, 2 left. R cubed times r squared to the 4th. Okay, so r cubed, that's power to a power. That's going to be r to the 3 times 3, which is 9. R squared to the 4th would be 2 times 4, 8. Now we have same base multiplication. This is where we add the exponents and we get r to the 17th. You may notice that as I'm going through this, I start with this one. This is the first one I check for is, are there parentheses? I deal with the parentheses first. Then if I have power to a power, I do that second, and then same base multiplication actually is what we do last. So we kind of looked at these properties and then I just did everything in reverse. In our last example before the challenge, we do want to do that distributive property. In the first set of parentheses, how many unique bases are there? If you said 3, you were correct. If you said anything else, the answer was 3. Right? 2 is its own base. It has its own exponent of 1. So we're going to multiply the exponent of 1 to 3, and this is going to be 2 cubed because 1 times 3 is 3. Then we're going to distribute to g squared. 2 times 3 is 6. And then we're going to distribute to h to the 4th. That's going to be h to the 12th. In the second set of parentheses, how many unique bases are there? That's right, there are 3 unique bases. 3 has an exponent of 1, and h also has an exponent of 1. So if you find it helpful to visually see the exponents, you would give those invisible ones, write those in, make them visible. 3 to the 1 times 2 would be 3 squared. G to the 4th squared would be g to the 8th, and h to the 1st squared would be h squared. From here, we're going to, so when we have normal numbers, we do normal number things. 2 cubed is 2 times 2 times 2, which is 8. And then I'm also going to, so I'm kind of going to use the associated property and move the 3 squared over, since that's another number. 3 squared is 3 times 3, and that's 9. And again, everything here is multiplication. So this is 8 times 9. Now I'm going to look for my same bases. And here I have g to the 6th and g to the 8th. So those are the same base. I have 6 factors of g. I have 8 more. That's a total of 14 factors of g. And then I have h to the 12th and h squared. I have 12 factors and 2 more. That's also 14 factors. And then that last but not least, we can multiply 8 times 9. That's a regular 8 and a regular 9 makes a regular 72. So we have 72 g to the 14th, h to the 14th. For our challenge, we want to write one expression, just one expression, using all 3 properties. And the simplified result is 18x to the 11th. Did you come up with anything? Here's just one of the infinitely many possibilities. What if we did 3x to the 4th squared? So this Here we're using distributive property. 3 squared is 9. X to the 4th squared is x to the 8th. And then what else do I need? So I've taken care of the distributive property and power to a power. Take that. I have 9. I need another factor of 2. I have 8 of the 11x's, and then I could just multiply by x cubed. So this would be one option. There are infinitely many that would multiply to and create an answer of 18x to the 11th. And even though this is a great stopping place, I actually want to do one more slide because these are some other properties that are really good to know. I've already talked about the first one, this typically invisible exponent of 1. A to the first is the same as if we just saw A, and then we could switch this around. A is the same as A to the first. So that's in these previous examples. When I didn't have an exponent, like 4 didn't have an exponent that we could see, it has an exponent of 1. A to the 0, this one's a little bit sneaky, but anything raised to the power of 0 except for 0 itself is equal to 1. And we'll get into that in the next video, why this one holds. But anything, so 5 to the 0 is 1. A to the 0 is 1. In parentheses, 1/2 x to the 1,000,000th, y to the -10th, all of that raised to the power of 0 is 1. And that's it, just as long as there's no zeros involved. And then 1 raised to any power at all is equal to 1. So that one's kind of just a little silly one, but it is true. These have been the first 3 properties of exponents plus a few bonus extras. Thank you for stopping by.